Welcome back to The Roots Survived. We're now in the dead of summer. Outside, the concrete is radiating heat like a furnace. The grass is turning brown. And inside your home, you're hearing one of the most expensive sounds in modern life. The deep, heavy hum of your air conditioner's compressor, working at its absolute limit. You know that sound, don't you? It's the sound of your hard-earned money disappearing straight into the power grid. Every year, heat waves seem to last longer, summers grow hotter, and that dreaded monthly bill from the electric company gets heavier. The average household can now spend hundreds of dollars just to keep the home livable from June through September. Cooling may account for only about 12% of annual electricity use, yet during the hottest summer months, it can surge to 30%, 40%, or even 50% of the monthly bill. Your compressor switches on, pulls 3,000 to 5,000 watts, and keeps running for hours, sending the electric meter spinning. Then, when you finally give in and call an HVAC company, what answer do you usually hear? Your system is old. It's a 10-SEER unit from 2005. You need to replace it. What you really need is our new high-efficiency, variable capacity system, with a better SEER rating, smarter home integration, and an installed price of only $8,000 to $14,000. But hold on, is replacement truly the only option? Do you really need to spend thousands of dollars on a brand new unit simply because summer is doing what summer has always done? What if I told you there is a simple and elegant principle of physics, supported by peer-reviewed scientific research since the 1970s, that can improve the efficiency of your current air conditioner, reduce your electric bill by as much as 40%, and be built in your own backyard in less than an hour for only $16? No new unit, no licensed contractor, no crushing debt, just a $16 coil of copper tubing, a few zip ties, a garden hose, and a basic law of thermodynamics that the $20 billion a year HVAC replacement industry would rather you never discover. In this video, I'm standing firmly on the side of the homeowner, the tinkerer, the survivalist, and the everyday person who wants to improve their home, gain real practical knowledge, and stop allowing utility companies to control their financial freedom. By the end, you'll understand the exact physics behind why your air conditioner struggles during a heat wave, how a slow trickle of water can help it perform like a system twice its price, and how to build the setup safely without damaging your expensive equipment. Let's dive in. Part 1. The heat wave struggle and the pain of the utility bill. Let's begin with a brutal reality that nearly every family experiences but rarely stops to examine. In May, you set your thermostat to a comfortable 74 degrees Celsius, and your electric bill might be around $80. Then July arrives. You keep the thermostat at that exact same 74 degrees Fahrenheit, but suddenly the bill jumps to $280. Why? The temperature you want inside your home has not changed. Your thermostat is still demanding the same target. The difference is not what is happening inside your house. It is the battle your outdoor unit is fighting against the surrounding air. Most people assume an air conditioner creates cold air. But in physics, cold is not actually a thing. It is simply the absence of heat. Your air conditioner is really a heat pump, a machine that collects heat from inside your living space, carries it outdoors, and releases it into your yard. And this is where the physical bottleneck begins. The hotter the air becomes outside, the harder it is for your outdoor unit to release that heat. Imagine trying to dry a soaking wet towel inside a steam room. Or picture yourself trying to pour more water into a glass that is already filled to the very top. The heat simply does not want to move. When the outdoor temperature reaches 100 degrees Celsius and climbs toward 105 degrees Celsius, or 41 degrees Celsius, the air surrounding your condenser is already packed with thermal energy. Your air conditioner is attempting to force even more heat into an environment that is already scorching. To make that happen, The compressor must squeeze the refrigerant gas much harder, raising both its pressure and temperature until it becomes hotter than the outdoor air. That additional compression comes at a serious cost. The compressor strains. Electrical amperage rises. Operating cycles stretch from 20 minutes into hours, and your electricity bill begins climbing dramatically. According to the Department of Energy's own thermodynamic data, for every degree the outdoor temperature rises above 95 degrees Fahrenheit, your air conditioner's cooling capacity falls by roughly 1%. At the same time, its energy consumption can increase by as much as 2% for every additional degree. That means on a blistering 110 degrees Celsius afternoon, a standard 5-ton central air conditioner can effectively be reduced to the performance of a 4.5-ton system, while drawing more electricity than it was ever intended to consume. It runs continuously, pulls maximum current, and still struggles to keep your house barely comfortable. The system is not failing because it is broken. It is failing because the surrounding heat is thermally suffocating it. So when an HVAC salesperson points toward your unit and says, "It's struggling, you need a $10,000 replacement," are they really telling you the entire truth? Or are they taking advantage of a basic law of physics that may be addressed for little more than the price of a couple of pizzas? Part 2. The refrigerant cycle. Why your AC chokes in a heat wave. To beat the system, we first need to understand how the system works. So let's break down the refrigeration cycle in clear, simple language. No academic lecture, just practical knowledge that will completely change how you look at refrigerators, automotive air conditioners, and heat pumps. The refrigerant inside your air conditioner is a chemical compound designed to boil at a very low temperature. It moves continuously through a sealed loop connecting two main coils, the evaporator coil inside your home and the condenser coil outside. Inside your home, the evaporator, the refrigerant enters the coil as a cold, low-pressure liquid. Warm indoor air is blown across the evaporator, and the refrigerant absorbs heat from that air. The cooled air is then pushed back into your rooms. Meanwhile, the refrigerant carries the absorbed heat away, boils, and changes into a warm gas. Next comes the squeeze, the compressor. That warm refrigerant gas moves outdoors and enters the compressor. The compressor forces the gas molecules tightly together. This compression raises both the pressure and the temperature, transforming the refrigerant into an extremely hot, high-pressure vapor. Then the refrigerant moves through the outdoor condenser. The superheated gas enters the condenser coil, while the outdoor fan pulls ambient air across the hot metal surface. As the refrigerant cools, it releases its heat into the outside air, condenses back into a liquid, and travels indoors through an expansion valve to begin the entire cycle again. This is where the laws of physics become incredibly unforgiving. The refrigerant can only condense back into liquid when the air outside is cooler than the refrigerant moving through the condenser coil. Heat naturally flows from hotter objects toward colder ones. So if the outdoor air is already 105 degrees Celsius, or 41 degrees Celsius, the refrigerant inside the condenser may need to reach 125 degrees Fahrenheit, or even 130 degrees Fahrenheit, before its heat can flow outward. To produce that extreme temperature, the compressor must generate enormous head pressure, and that pressure places an equally enormous load on the compressor motor. Now look at the hard data from a standard experimental evaluation of split-system air conditioning performance. Scientific research shows that when the outdoor dry bulb temperature increases by only 1 degree Celsius, the compressor's required electrical input rises by an average of 1.4% to 1.6%. At the same time, the unit's actual cooling capacity falls by approximately 0.8% to 1.0. Because the system is consuming more electricity while producing less cooling, its overall coefficient of performance, or COP, the standard measurement of how efficiently an air conditioner converts electricity into cooling, drops by an astonishing 1.95% to 2.1% for every single degree Celsius the outdoor temperature rises. This is why, during the most intense summer heat waves, the temperature of the refrigerant discharged from the compressor can climb close to 100 degrees Celsius, or 212 degrees Celsius. The compressor is operating under a punishing combination of extreme pressure and extreme heat. But what if we could trick the condenser? What if we could make the outdoor unit behave as though it were operating on a cool 75 degrees Fahrenheit, or 24 degrees Celsius, spring afternoon, even while the actual temperature outside is a brutal 105 degrees Celsius? If we lower the temperature of the air reaching the condenser coils, the head pressure falls almost immediately. The refrigerant can condense more easily, the compressor draws significantly less electrical current, and the cool air flowing from the vents inside your home returns to maximum strength. So how can we accomplish that without constructing a giant air-conditioned shelter around the outdoor unit? For the answer, we must look back at a secret discovered by desert civilizations thousands of years ago. Part 3. The Ancient Secret of Adiabatic Cooling. Before discussing copper coils and modern electronics, let's travel back through history. Long before humans discovered electricity, people survived in some of the harshest, driest, and most brutal deserts on Earth. Yet these ancient cultures found remarkable ways to keep both themselves and their food cool. Deep in the Persian desert, in the ancient city of Yazd, engineers built magnificent towers, known as badgirs, or wind catchers. These structures captured hot desert winds high above the ground and directed them downward toward underground water channels, called qanats. As the dry air passed over the moving water, part of that water evaporated. During this process, the hot air surrendered its thermal energy, allowing its temperature to fall by 20 to 30 degrees Fahrenheit before it entered the city's homes and gardens. Beside these badgirs stood structures known as yakchals, enormous cone-shaped domes built from mud brick. Through the combined physics of evaporation and thermal radiation, these structures could create and preserve ice, even during the middle of summer. In ancient Egypt and Rome, servants hung damp reed mats or wet cloth across doors and open windows. As the hot, dry breeze moved through the wet material, it entered the living spaces as a cool and refreshing mist. Desert travelers across the Middle East and Africa also stored drinking water inside porous clay containers, called zir pots. Water slowly passed through the tiny openings in the clay, evaporated from the pot's outer surface, and cooled the water that remained inside until it felt noticeably cold to the touch. How did they achieve all of this without consuming a single watt of electricity? They used a fundamental property of water called the latent heat of vaporization. Water is an extraordinary substance. It possesses one of the highest heat capacities among the common liquids found on Earth. But its true superpower is the enormous amount of energy required to change it from a liquid into a vapor. Raising the temperature of 1 gram of liquid water by 1 degree Celsius requires only 1 calorie of heat. But converting that same gram of water completely into vapor requires an incredible 540 calories of thermal energy. In imperial units, evaporating only 1 pound of water absorbs approximately 970 BTUs of heat directly from the surrounding environment. That heat energy does not simply disappear. It is absorbed by the water molecules, allowing them to break free from their liquid bonds and escape into the air as vapor. And where does this enormous amount of energy come from? It is pulled directly from whatever the water is touching, the surrounding air, a metal surface, or even your own skin. This is why you can begin shivering after stepping out of a swimming pool on a windy day, even when the weather is hot. The water evaporating from your skin is literally carrying away your body heat. In modern thermodynamics, this process is called adiabatic cooling, also known as evaporative cooling. When a fine mist of water is introduced into a stream of hot, dry air, the droplets evaporate almost instantly, absorbing the latent heat of vaporization directly from the air. The air's dry bulb temperature falls dramatically, while its relative humidity rises. If the air approaching your condenser is 105 degrees Fahrenheit, and we guide it through an active evaporation zone, its temperature can easily fall by 15 degrees Fahrenheit to 30 degrees Fahrenheit before it ever reaches the aluminum fins of your outdoor unit. Your air conditioner is no longer attempting to release heat into an intensely hot, saturated atmosphere. Instead, it is releasing that heat into air that has already been chilled through the natural physics of evaporation. Part 4. The condenser pre-cooler. Proven science versus the replacement cartel. At this point, you may be wondering, this sounds like an impressive DIY trick, but is there solid scientific evidence showing that it actually works with modern residential air conditioners? The answer is yes. The data is overwhelming, and it has been published in some of the world's most respected engineering journals. Let's begin with a landmark study conducted by researchers at Anna University in Chennai, India, and published in the peer-reviewed journal Scientific Reports. The researchers took a standard residential split-system air conditioner and modified its outdoor condenser with an adiabatic pre-cooling system. They then tested how cooling the condenser's intake air affected the system's efficiency under hot and humid conditions. The results were astonishing. After cooling the air entering the condenser, the system's coefficient of performance rose from a baseline of 2.8 all the way to 5.0. That represents an incredible 78% improvement in cooling efficiency. At the same time, the machine's overall energy consumption fell by an average of 39.2%. Think about what that means. A 39% reduction in electricity consumption could reduce a typical $300 summer cooling bill to approximately $180, all because of one simple pre-cooling method. Another extensive evaluation was carried out by the Florida Solar Energy Center, or FSEC, under the leadership of senior researcher D. Parker. The research team designed and tested an evaporatively cooled mini-split condenser across complete summer seasons. Their rigorous testing demonstrated a 21% seasonal improvement in energy efficiency, even in Florida's famously hot and humid climate. More impressively, when the outdoor temperature reached a peak of 35 degrees Celsius or 95 degrees Celsius, the pre-cooling system improved cooling efficiency by almost 50%. FSEC researchers also calculated the system's water consumption, which averaged a modest 22 liters each day. If the pure condensate dripping from the indoor evaporator coil is collected and redirected to the outdoor pre-cooler, the amount of municipal water required can fall to less than 4 liters per day. Simulations using European climate data indicate that the seasonal savings become even greater in hotter and drier regions. Madrid, Spain, 50% seasonal savings. Sevilla, Spain, 46% seasonal savings. Athens, Greece, 36% seasonal savings. Lisbon, Portugal, 33% seasonal savings. So why is this technology not built into every air conditioner sold at the local hardware store? Why does it not appear anywhere on a standard HVAC price list? The reason is the economics of the replacement cartel. The residential HVAC industry in the United States alone is an enormous $20 billion a year machine. Its main source of profit is not selling you a $30 accessory that helps your existing equipment operate more efficiently. Its profit comes from selling you an entirely new system. A technician who arrives at your home in July is trained, encouraged, and often paid a commission to tell you that your air conditioner is old and must be replaced with a modern, high-SEER unit. But here is what they will not tell you. A 12-SEER air conditioner operating with a pre-cooled condenser can actually outperform a brand-new 16-SEER unit that is forced to operate in raw, scorching outdoor air during the hottest afternoon of the year. SEER rating systems evaluate air conditioners as they leave the factory under dry and standardized laboratory conditions. They do not measure what happens when you change the microclimate around the outdoor condenser. A $16 DIY copper coil, combined with a slow trickle of water, could give your existing air conditioner another 5 to 10 years of efficient, low-stress operation. But a $16 solution does not create a $5,000 invoice, and that is why this science remains quietly buried inside engineering journals. Part 5. The $16 die copper coil build, step by step. All right, it's time to roll up our sleeves and build a basic evaporative pre-cooling system for less than $30. First, let's go through the materials. You should be able to find everything in a single visit to your local hardware store. 10 to 20 feet of flexible, quarter-inch soft copper refrigeration tubing. At current prices, this should cost around $16 to $20. One pack of UV-resistant zip ties costing about $4. A garden hose splitter fitted with a needle valve or a basic brass drip irrigation valve for approximately $6 to $10. And a strip of cotton or burlap fabric that will serve as a wick. That's all you need. Even when every component is purchased brand new, the total material cost should remain below $30. The entire system can be assembled in roughly 45 minutes. Step 1. Form the copper coil. Take the soft copper tubing and carefully bend it into either a flat spiral or a cylindrical coil. The most important rule here is to work slowly. Wrap the tubing around a smooth, rounded object, such as a paint can, bucket, or cooking pot. This helps prevent the copper from kinking. A kink will restrict the flow of water, increase pressure inside the line, and choke the entire system. Your goal is to create a flat, orderly coil that roughly matches the dimensions of the air intake grills on your outdoor condenser. Step 2. Secure the coil position, the copper coil against the air intake side of the condenser. This is the section where the fan draws outdoor air inward through the aluminum fins. Use the UV-resistant zip ties to fasten the tubing to the unit's protective outer grill. Leave approximately 1 inch of space between each loop, so the copper does not block or restrict airflow entering the condenser. Step 3. Add the wick. Wrap the cotton or burlap material around the copper tubing. The fabric will function as a capillary wick. Without it, water flowing across the smooth copper surface would simply gather into large droplets and fall directly onto the ground, contributing very little to the cooling process. The fabric holds moisture against the metal and spreads it across a much larger surface area. This allows nearly every section of the coil to evaporate water into the incoming airflow. Step 4. Connect the water supply. Use a short section of vinyl tubing and a basic hose barb adapter to connect one end of the copper coil to your garden hose. Connect the water supply through the hose splitter and needle valve so you can control the flow precisely. Leave the discharge end of the copper tubing open, allowing excess water to drip onto the concrete pad or into a nearby drain. Step 5. Calibrate the flow. Turn on the outdoor faucet and slowly adjust the needle valve. The goal is not to flood the condenser. You want only a slow, steady trickle, just enough to keep the fabric wick consistently damp. A flow rate of approximately 1 to 2 gallons per hour is the ideal range. This produces a thin film of moisture that evaporates as the condenser fan pulls hot air through it. The evaporation lowers the temperature of that air before it ever reaches the air conditioner's coils. It sounds simple, doesn't it? And it is. But before you rush outside carrying a pair of pliers, we need to discuss the serious and potentially expensive engineering dangers hidden inside a cheap DIY installation. Without understanding water chemistry and compressor physics, you could destroy a $5,000 air conditioning system in a single summer. Part 6. The dark side. Corrosion, scaling, and killers Search for AC misting systems on forums such as Reddit's RHVAC Advice or RDIY, and you will find what looks like a battlefield filled with angry HVAC technicians warning homeowners to stay away. One technician described a client who destroyed a $250,000 industrial chiller simply by placing an ordinary lawn sprinkler beside it. Another homeowner documented a $5,000 mistake after a cheap misting kit corroded a brand new residential air conditioner in less than 3 years. Why would a technology demonstrated in government research laboratories destroy equipment in real-world use? The answer comes down to two critical issues: water chemistry and galvanic corrosion. First, consider the chemistry of the water. Municipal tap water and well water are not pure H2O. They contain dissolved minerals, especially calcium carbonate and magnesium. When untreated tap water is sprayed or misted onto a hot condenser coil, the water itself evaporates into the air. The minerals, however, cannot evaporate. They remain behind on the metal surface. Over the course of a single cooling season, these deposits can develop into a thick white crust known as limescale or calcification. Calcium carbonate is an extremely effective thermal insulator. Once it coats the condenser, it interferes with the movement of heat from the refrigerant inside the coil into the surrounding air. This creates a destructive paradox. You installed a pre-cooler to reduce energy consumption, yet the mineral scale created by that system begins insulating the coils and making heat transfer even worse. The compressor must then work harder and run longer. Eventually, the compressor motor may burn out completely. The second danger involves metallurgy and galvanic corrosion. The outdoor condenser contains copper tubes surrounded by delicate, extremely thin aluminum fins. When copper tubing is placed directly against aluminum and mineral-rich water is introduced, you have unintentionally created a galvanic cell, a primitive battery. In galvanic chemistry, when two different metals come into contact in the presence of an electrolyte, such as mineral-containing water, an electrical current begins flowing between them. The less noble metal, which in this case is aluminum, becomes the sacrificial anode and starts dissolving. Those thin aluminum fins can corrode, discolor, and eventually crumble into dust within a matter of months. Once the fins break apart, the condenser loses the large surface area it needs to release heat, and the air conditioner is ruined. Municipal water also contains chlorine, which aggressively attacks the protective oxide layer on aluminum and accelerates corrosive pitting. Then there is one final and serious thermodynamic danger: liquid slugging inside the compressor. Your compressor is engineered to compress gas, not liquid. If the DIY pre-cooler continues operating during a mild, humid 80 degrees Fahrenheit day, it can reduce the condensing temperature and pressure far below the proper operating range. When head pressure becomes too low, the refrigerant may no longer have enough force to move correctly through the expansion valve. It may fail to evaporate completely inside the house, allowing raw liquid refrigerant to travel back through the line and enter the compressor. Liquids cannot be compressed. As a result, the returning refrigerant acts like a hydraulic hammer, capable of instantly destroying the compressor's internal valves, pistons, and scroll plates. Does that mean the entire technology is a scam? No. It means the system must be built like an engineer would build it, not like a careless hack. Part 7. The sustainable engineering way to do it right. To capture the potential 40% energy savings of adiabatic cooling without destroying your air conditioner, you must follow 4 strict engineering control principles. 1. Maintain a safe physical distance. Never wrap copper tubing directly around the aluminum fins of the condenser, and never spray water mist directly onto them. Commercial pre-cooling systems use separate supporting frames positioned approximately 50 to 55 centimeters away from the condenser surface. By installing the pre-cooling material at a distance, You give the water mist enough time to evaporate completely before the airflow reaches the condenser. The air entering the machine is cooler and contains water vapor, but liquid droplets and mineral deposits never come into direct contact with the metal components. Without liquid water touching the condenser, there is no scaling and no galvanic corrosion. Recycle the air conditioner's condensate. Where can you find a free supply of clean water without dissolved minerals? Look at the indoor evaporator coil. As your air conditioner cools the house, it also removes humidity from the indoor air. Gallons of atmospheric moisture can condense on the cold evaporator coil. This condensate is essentially distilled water. It contains none of the dissolved calcium, magnesium, or other minerals normally found in tap water. You can route the indoor condensate drain into a small collection tank outside, then use a tiny low-power pump to circulate this water through the pre-cooler. By reusing condensate, you can completely eliminate the threat of mineral scaling. 3. Install an automatic solenoid valve. One of the biggest mistakes in cheap DIY systems is allowing the water to flow continuously, even after the compressor has switched off. This wastes water and leaves the surrounding area constantly damp, creating an ideal breeding ground for mold. The solution is a simple and inexpensive 24-volt AC solenoid valve. Connect the solenoid wiring in parallel with the 24-volt control signal inside the outdoor unit, the cooling and ground terminals responsible for activating the compressor contactor. When the thermostat calls for cooling, the 24-volt signal activates both the air conditioner and the solenoid valve at the same time. Water begins flowing the moment the compressor starts and stops the exact second the compressor shuts down. Not a single unnecessary drop is wasted. 4. Use smart temperature control. The pre-cooler should operate only when the air conditioner is truly struggling against extreme outdoor heat. Install a simple inline bimetal thermal switch or a digital thermostat and set it to activate at 30 degrees Celsius or 86 degrees Fahrenheit and above. When the outdoor temperature is only 80 degrees Fahrenheit, the air conditioner can handle the conditions easily without assistance. The thermal switch keeps the pre-cooler turned off, preventing head pressure from falling too low and removing the risk of liquid slugging in the compressor. But as soon as the afternoon temperature climbs above 86 degrees Fahrenheit, the switch closes, the water begins flowing, and the system receives thermal relief at the exact moment both the air conditioner and the electrical grid are under the greatest strain. Conclusion. So let's step back and consider the larger picture. We live in a world that constantly tells us the only answer to our housing and energy problems is to consume more, to discard older machines that still function, spend thousands of dollars on complicated replacements, and lock ourselves into endless service agreements and rising utility bills. But as we have seen, some of the most powerful solutions are not hidden inside glossy high-tech brochures or expensive sales presentations. They are found in the elegant and simple laws of physics that desert civilizations mastered thousands of years ago. The power released when water changes state, and the thermal conductivity of an ordinary metal tube. With the right knowledge, a $16 coil of copper can transform an existing air conditioner into a highly efficient cooling system, cutting the summer electric bill by as much as 40%, without requiring a single visit from a contractor. But remember this: knowledge without precision can be dangerous. If you decide to build this system, build it like an engineer. Keep the pre-cooler at a safe distance. Reuse the condensate from the indoor unit, control the water with a solenoid valve, and respect the metallurgy of the equipment. That is the path toward genuine self-reliance, improving what we already own, understanding the physical world around us, and taking control of our homes one weekend project at a time. If you enjoyed this deep exploration of home optimization and practical energy savings, subscribe now and become part of our community here at The Roots Survived. Every week, we test inexpensive and clever DIY projects, and we always ground our guides in real scientific data. Now tell me in the comments, would you build an Adiabatic condenser pre-cooler this weekend, or will you continue paying the full price of raw electricity? Until next time, stay curious, keep building, and remember, you do not need to purchase a new machine to live comfortably. You simply need to master the physics of the machines you already own.